Robot Combat League is a show that basically equips human athletes with giant robotic avatars, and they fight. They fight basically to the death in the arena. But of course, the robots are doing the bleeding and the dying, and the athletes are doing the controlling of the robots. The athletes get into a thing I call the exosuit, and there's two of them, sort of a jock and a tech. It's kind of how I look at it. And the jocks get into these suits that are motion capture suits, sort of a precision mechanical device, and it captures the movements of their arms and their torso. And the tech has a control pod where they use like flight controls, sort of like flight controls, to navigate the robot around in the arena. So they're algorithmically controlling the walking of the robot, while the jocks are, with direct mapping, controlling the movements of the arms and torso of the robot. And
wow.
So the jocks can use their, if they have experience as fighters, some of them are MMA fighters, they can apply that, that muscle memory in the fight. I've been building animatronic creatures for the film industry since I was 19, and I started out in Marin County working for George Lucas's company, ILM. And in the mid-90s, I got involved I was invited to compete in an event called Robot Wars, which was this sort of, at the time, this sort of underground engineering challenge where people from all over the world would actually bring machines that they had built and they'd fight in a ring. And the machines were, it was open competition, so the machines could be whatever you wanted within a certain weight range. And that I was the heavyweight champion of Robot Wars for a while. And that evolved into BattleBots, and I competed at BattleBots for many years as well. And I love the engineering challenge of it and the design challenge. And I met a lot of people from outside the effects industry who came from all sorts of different backgrounds. Some of them came from scientific backgrounds. Some of them were, farm equipment people. And it was just an incredible scene. And that really led to my work in legitimate robotics, like, for example, bomb squad robots. But my real passion has been entertainment robotics. And I've been working in that field and trying to elevate that field for my entire career. Well, it really depends on, the design process really depends on what it is that I'm trying to do. In the case of Robot Combat League, there were several sort of design stages. One of them was really thinking about, what is the final product? What are we going to see? We're looking at a screen, and there's action occurring on the screen. And I wanted to see robots that could run and punch and have all this action and destruction. I wanted them to be very connected to their human operators. And so I sort of broke it down into pieces. There's the design of the arena, there's the design of the control platforms, there's the design of the robots themselves. In the case of the robots, it becomes something of a process of elimination, because the human body is so complicated that you really can't imitate it entirely. So I had to decide what is the minimum number of joints and mechanical actuators you need to make a robot that can walk and punch. And I came up with a number of 22. So from that, I had a place to start. So I began designing the robot. I had a sketch, a single sketch that gave me sort of the rough proportions. And honestly, I agonized over it quite a while, because the weight and the size and the proportions and the force of the actuators and the flow of the fluid into the actuators of the hydraulic system, they're all interrelated. And you have to kind of dial this in. Since I didn't have a lot of time, I really had to make sure that decisions that I were making were correct. Because making mistakes is a big part of the design process. And when you have very little time, you have to make as many mistakes as possible in a short time as you can. So, and when you build on the scale, a mistake can be quite costly. So I did spend quite a lot of time working in CAD on the robots. I didn't really do any simulation, but the robot existed completely in CAD at a certain point, even though I was already making portions of it as the model was evolving. But the CAD process was very important to that. I'm using Autodesk Inventor to do all my mechanical design, and I also use I designed the whole robot in Autodesk Inventor, including some of the more cosmetic parts, like the sheet metal that forms the body of the robot. Think about the design of the robot a little bit like a car. There's sort of a chassis, sort of understructure, and then there's the sheet metal that gives it its character, its appearance. And in the case of these robots, the sheet metal was 18-gauge steel, or in the case of the prototype, it was 20-gauge stainless steel. And I have a program called Lamina, and I'll take the Inventor model of, let's say, the shoulder, for example, and I'll export that as a surface model. and then I'll pull that into Lamina, and Lamina will take the surface model, this very sort of curvaceous-looking thing, and split it open and flatten it out into a flat pattern. That even has registration notches all along the edges of the parts. They go together like a jigsaw puzzle, so you get this sort of perfect seam when the pieces go together, and you weld it. And it's really, if you like doing jigsaw puzzles, it's really quite satisfying to make these things. But you know, it's a form of software that takes advantage of certain manufacturing techniques. In this case, a water jet cutter. A water jet cutter is a machine that can cut sheet metal or even very thick metal. It's fairly inexpensive, and it's great. The edge is pretty good, certainly good enough to weld. And having these pieces made is not, you know, it's accessible. So this is to me, a very accessible way of doing kind of large-scale sheet metal structures on top of a frame affordably and very quickly. You know, I think about the anatomy of the robot a little bit like human anatomy. They're hydraulic, so they have these hydraulic linear actuators that are kind of like muscles. There's this fluid system that delivers that physical power to those muscles. There's feedback, electronic feedback that measures the position that comes back into the brain of the robot. The brain is actually a PC-104 stack with power supply card, digital analog conversion, analog to digital conversion, a processor. And that whole unit is in the very center of the robot, surrounded by a custom manifold that has all the valves. So in the very core of the robot, there's this brain, there's a manifold, which is kind of like the heart of the robot, all the servo valves that give it the ability to move with precision. And what that PC-104 stack is doing is it's closing the servo loop. So it takes a command from the control computer, reads that command, sends a signal to the valve, which either opens and closes, depending on the position of the cylinder, which is being measured by a potentiometer. So this loop is constantly going, where it measures the cylinder, listens to the command signal, and then does whatever it needs to do to make that cylinder go to that position that you're telling it to go to. And it does that 480 times a second. And then on the control side, there's more like a PC that's running real-time Linux, and that is taking all of this control information that's coming from the suit that's capturing the movements of the athlete, and it takes that data and it, for example, for the motion base, it translates the twist and roll of the jock's body, and it translates that into the 6 linear servo commands you need to control the motion base, the 6-axis motion base. And it also sends commands to the shoulders and the elbows to make the arms do whatever they're supposed to be doing. I did build an electric servo, using servos I had lying around. I did build a 6-axis motion base to give me a sense of just the size and the feeling of how this thing was going to be in person. But I really, you know, it's a tough thing. That robot was made over the course of 4 months. The prototype was made over the course of 4 months, and sometimes I would do big sort of cardboard cutouts that I could just hold up and walk around, and get a sense of what is its stance, what is its how much, you know, does it impose itself into a space. The way the competition works is there are 12 robots, and it's a single elimination fight. So what typically happens is, let's say the first match, you know, a robot is beaten, and both robots are damaged in the course of the fight, some more than others, and it depends on the fight. Some of the fights were pretty horrific, and some of the robots were kind of okay at the end. Be that as it may, the loser becomes an organ donor for the rest of the robots. Okay. So as the show progresses, we're stripping parts out of the dead robots and keeping the survivors alive. And sometimes, you know, at the end of a fight, both robots can be really badly damaged. So I'm sending actuators back to the manufacturer to have them repaired and brought back again, put back into service. In general, the way I engineered the robots, the stuff that was breaking was stuff that I could buy and replace, as opposed to things that I had made from scratch that then I would have to remake to replace. So it's a little bit preferable to have that sort of situation.
So you're designing for disassembly destruction.
You know, it's an engineering challenge that you know, you chase failure around. You know, if you make something a little stronger, then that won't break anymore. Now something else is going to break. And engineers talk about this. I feel like a perfectly engineered system the entire thing will fail simultaneously, when it fails. And I've actually seen that happen. But that's not what I wanted to have happen here. I wanted to have failure occur in a very predictable place that was somehow beneficial to me, either in the part that was breaking is a part that I can replace, or in the context of the show, when that part breaks, you can really tell something spectacular happens when this piece fails. It's not like, well, something broke, and after the match, it's like, it didn't seem like it was working very well, and you look at it, it's like, oh yeah, that's bent or that's cracked. You don't want to discover that later on. You want it to be obvious during the fight. Not exactly, no. I mean, these machines are really designed especially for this entertainment spectacle, and there's not a lot of development time for something that's for a TV show. So I built 12 of these robots in 4 months.
Wow.
Not a lot of time to really develop a lot of high-tech features on these things. But going forward, I now have a platform that I can build upon. So these are the Model Ts, and my goal is to get to Formula One. And right now we're still, we've still got these kind of jalopies, and I want to keep improving them continuously to the point where we get machines that are freestanding and can, basically run around and do roundhouse kicks and stuff like that. The prototype is named Hades, and that's my robot. And there are 12 others that were in the show, and they're all in various states of disassembly right now. Well, I already see home-based robotics building and people using personal 3D printers to make all kinds of stuff. I started using a 3D printer in 2004, and I was fortunate to have access to a big, industrial machine, a big FDM machine that prints polycarbonate. And I built a bunch of stuff with this. And the learning process, because people have the idea, well, you can print anything with a 3D printer. You can't exactly. There's definitely an art to getting good parts out of a 3D printer. And it takes experience. And you're not really going to get that experience if you send a file to Shapeways and you get it back. It's like, it's not quite what I thought it was going to be, and you send the file again. If you actually have a MakerBot or even something that's even cheaper than that, but a comparable machine, the fact that we can just buy these machines and have them in our homes, that's fantastic. And I think you're going to see an explosion of interest in that, and an explosion of people thinking about that design process and how to really get the most out of those machines. And then if you have a person who's got a MakerBot at home, and all of a sudden they have access to a Fortis or something like that, then they're going to be able to walk into that situation and say, okay, I can rock this thing. Let's make some really cool stuff. In Robot Combat League, the robots basically use 3 very specific processes. I have my own CNC machine, so a lot of the parts are CNC'd out of aluminum alloy, parts that need to have things like bearings pressed into them, and there are a lot of large plates, thick plates of aluminum that are cut on a water jet cutter. And some of those plates have been Blanchard ground, which is basically you run it through these 2 huge discs, and you can bring a piece of metal to a precise thickness. So the thing about combining Blanchard grinding with water jet cutting is you get a part that's just about as precise as something that came off a CNC machine, except for the perimeter edge. So if you're screwing stuff onto the surface, it's fantastic, and not too expensive. And you can make really big stuff very quickly. And then the third technique is this process of going from a surface model into lamina, water jet cutting sheet metal, and then rolling those pieces and recreating these large 3-dimensional shapes by welding the sheet metal together. There are so many cool robot kits you can get. That's a really great way to start. In my case, I was really interested in like making mechanical creatures or making things that moved in some organic way. And so I was making like puppets, but I started very small, and I was using basic materials. And if you're working small, then if you make a mistake, you really haven't spent a lot of money or even a lot of time on what you're doing. And don't be afraid of that mistake-making process, because that's really how you learn. When I made this little mechanical head, the very first mechanical thing that I made, that actually got me a job at ILM. I remade the eye mechanism for it 10 times. It was made of bent wire. And I keep working this material over and over again. I went through a whole spool of wire. But when I was done, I was an expert at bending wire, and I could make a perfect little part, a mechanical part that would work. But the material is cheap, and it didn't take a lot of time, and I could just use a simple tool to do it. But that was a good foundation, and now I have the confidence to make something bigger. And now, because of my experience with BattleBots, I know so much firsthand about just the behavior of materials in really hostile environments that I can go ahead and I can make something like Robot Combat League robots and be confident that I'm making the right choices as I move through that engineering process. Making stuff is really important, I think. I mean, book learning is extremely important as well, but that wasn't the path that I followed. I followed a path of doing one thing and then doing another thing and learning and keeping on adding techniques and resources to my toolkit, if you will. I don't know, but I'll tell you, in 5 years' time, I will have chosen 5 more challenging things to try, and who knows what technology will be available at that time. Robot Combat League was my first hydraulics project, so I've got a taste for making big hydraulic stuff now. Maybe my next project will be, I don't know, plasma inductor phase, blah, blah, blah. I don't know. I don't know what I'm going to be doing in 5 years.
Space travel.
I'm looking forward to whatever it is. Class is always in session for me, and I'm always looking for something that's going to elevate my art form.
A production of EVD Media.